Hi, I'm Yang-Jae Lee. I'm going to present you our work, MFNeRF, Memory Efficient NeRF with Mixed Feature Hash Table. Novel view synthesis is one of most popular computer vision tasks that generates unseen images of specific objects or scenes from a set of images. Recently, the emergence of neural networks has significantly improved the quality of novel view rendering. The pioneering work in this field is the neural radiance field, known as NeRF. It represents 3D space as a radiance field and trains two MLPs to learn the radiance distribution. Using a volume rendering technique, it generates high-quality novel view images that include view-dependent lighting effects predicted by the MLP. However, its core, a deep and wide MLP, not only significantly slows down inference speed but also introduces long training times and high memory usage, limiting its suitability for real-time applications. Recent follow-up studies have proposed employing efficient data structures, such as feature grids, to store intermediate scene representations. Instant NGP introduced multi-resolution feature grids combined with a lightweight MLP to accelerate inference speed to near real-time. However, encoding intricate scene details requires dense, fine-grained grids, which demand large amounts of VRAM, posing another bottleneck for the model. To further enhance the efficiency of NeRF, we propose MFNeRF. First, we conjecture that consecutive pairs of grids in multi-resolution grids share similar feature information for the same point, as all grids essentially overlap the same scene volume. Therefore, we hypothesize that a portion of the grids can share their storage for feature information. Based on this insight, we develop a novel approach that encodes multi-resolutional feature information into a single hash table, which we call mixed feature hash encoding. More specifically, we construct L multi-resolution feature grids and M hash tables, mapping each consecutive L, M feature grids to a single hash table. This mixed scheme allows corners at the same spatial location across feature grids to share feature information, i.e., mixed feature, effectively reducing the memory required for the hash tables. To ensure accurate storage and retrieval of the same spatial location across feature grids at the same entry in the mixed feature hash table, we transform the index of the current grid to the canonical indexing space within the group. The canonical indexing space corresponds to the grid with the finest resolution in the group. By applying a spatial hashing function to this transformed index, we can then locate the correct entry in the mixed feature hash table for the queried point at the grid level. Similar to instant NGP, after retrieving the feature vectors from the hash tables, we use a lightweight MLP to predict the color and density of the queried point. Then, using the alpha blending technique, the final pixel color is determined. During training, both the mixed feature hash table and the lightweight MLP are optimized using L2 loss. We benchmarked state-of-the-art methods on a single NVIDIA A6000 GPU using the synthetic NeRF and MFNeRF 360 datasets. To measure the efficiency of the model, we define a new metric, PSNR times FPS, megabyte. This metric demonstrates that MFNeRF performs more efficiently than other baselines, as you can see in the right figure. In other words, our method achieves faster performance with high-quality rendering while maintaining a constrained model size. Moreover, according to our ablation study, we find that when mapping more grids to the same hash table, in other words, when decreasing the number of hash tables M, the model's inference speed increases. We observe that when M is 8, MFNeRF demonstrates the best PSNR performance. Furthermore, the size of the hash table T is also a factor. We tested multiple settings for T and observed that increasing T enhances the rendering quality in terms of PSNR while requiring more storage. This indicates that we can further optimize the model by increasing the hash table size while mapping more feature grids to the same hash tables. Thank you for listening to the presentation.